For decades, the history books have told us which machines succeeded and which failed. The narratives are clean, the lessons clear. Steam turbines in locomotives? A dead end. Too complex, too heavy, too impractical for the brutal realities of railroad service. The experiments of the 1920s and 1930s proved it beyond doubt. Swedish engineers tried with the Ljungström turbine and watched it consume coal faster than it could haul freight. British railway workshops built prototypes that spent more time in repair shops than on the rails. By the late 1930s, the verdict seemed final. Turbine locomotives were an interesting curiosity, a theoretical possibility that crumbled under the weight of practical engineering. The reciprocating steam engine, for all its limitations, had won. That story, repeated in engineering textbooks and railroad museums, held firm for generations. But buried in the archives, a different story waits. Soviet technical journals from the 1920s, yellowed and rarely accessed, contained detailed specifications for a turbine locomotive that ran on German rails before being quietly dismantled and forgotten. Pennsylvania Railroad internal memos from 1944, filed away in museum storage, referenced design studies of European turbine experiments without naming sources. Patent applications from the 1940s and 1950s cite prior art in language carefully chosen to acknowledge influence without giving credit. The silence is louder than any official report when engineers copy a design, when railroads build machines that mirror the configuration of an earlier experiment, when the blueprint similarities are too precise to be coincidence. The archives begin to whisper what the history books will not say. Hidden among these scattered documents is proof of an engineer whose experimental turbine locomotive was dismissed as a dangerous failure by his contemporaries. German railway officials called it impractical. British observers wrote it off as an expensive dead end. Even supporters admitted it had severe problems with weight, complexity, and reliability. The machine was scrapped within a few years, its creator's name fading from memory as the conventional wisdom hardened. Turbines in locomotives were a failure. Everyone agreed. The chapter was closed. Yet 2 decades later, Pennsylvania Railroad unveiled a steam turbine locomotive that bore remarkable similarities to that forgotten experiment. The configuration, the approach to condensing steam, the philosophy of eliminating reciprocating motion all echoed designs from that earlier machine. A few years after that, Chesapeake and Ohio built their own turbine locomotives, again with design elements that seemed to trace back to the same source. Then Norfolk and Western joined the pattern. Each railroad claimed independent development. Each engineering team insisted their work was original. But the blueprints tell a different story. The condenser placement matches. The turbine mounting configuration mirrors the earlier design. The approach to converting turbine rotation into tractive effort follows the same logic worked out in Germany 20 years before. If the original experimental turbine was truly the dangerous failure that contemporaries claimed, why did 3 major American railroads quietly build machines based on its core principles? If the design was fundamentally flawed, why did Pennsylvania Railroad engineers spend months studying European technical reports from the 1920s before beginning their own turbine project? If there was nothing to learn from that failed experiment, why do patent filings from the 1940s carefully cite European turbine art without naming the engineer who pioneered it? The paradox demands investigation. Success in engineering is measured in numbers, in performance data, in machines that prove their worth on real tracks under real conditions. Failure leaves nothing but cautionary tales. Yet here is a machine declared a failure that somehow shaped the turbine locomotives built by some of America's most powerful railroads. Here is an engineer dismissed and forgotten whose ideas appeared uncredited in designs that followed. The story the archives tell does not match the story the textbooks teach. Somewhere between the official verdict of failure and the quiet copying that came after, the truth waits. The question is not whether the experimental turbine failed. The question is what failure means when your critics build copies of your work 2 decades later and call it innovation. The answer requires looking past the legend of failure to the engineering reality buried in test reports, patent files, and the remarkable silence that surrounds a name history chose to forget. The trail begins in places most railroad historians never look. Soviet technical journals from 1924 and 1925, published in German for international distribution, contain detailed engineering specifications and performance data for a turbine locomotive that ran on German rails. The diagrams are precise, the measurements exact. Weight distribution charts show a machine exceeding 200 tons. Turbine specifications list rotational speeds between 6,000 and 12,000 revolutions per minute, numbers that dwarf anything a reciprocating steam engine could achieve. The condenser system, essential for recovering steam and maintaining water supply, added more than 40 tons to the overall weight. Every technical detail was documented, published, and available to any engineer who cared to search for it. Fast forward to 1944. Pennsylvania Railroad internal correspondence, preserved in archive boxes at the Railroad Museum of Pennsylvania, reveals something unexpected. Engineering staff requested access to European technical literature on steam turbines. Specific references appear to German experiments from the 1920s. The memos are careful, the language precise, but the pattern is clear. Before Pennsylvania Railroad committed millions to building their own turbine locomotive, they studied what had been tried before. The documentation exists. The timeline is undeniable. Patent filings add another layer to the puzzle. United States Patent number 2,458,461, filed by Pennsylvania Railroad engineers in 1946, cites prior European art in its claims. The language is standard legal terminology, acknowledging that certain elements of the design build on earlier work. But the citations are oddly vague, referencing European turbine experiments without naming specific engineers or machines. It is the kind of careful wording that signals awareness without attribution, knowledge without credit. What the data should show, if innovation truly happened independently, is divergence. Different engineers facing the same problem should arrive at different solutions, especially when working decades apart in different countries under different constraints. Yet the blueprint similarities are striking. The fundamental challenge of a steam turbine locomotive remains constant across all attempts. A turbine needs to spin at thousands of revolutions per minute to operate efficiently. A locomotive needs to start from a standstill and deliver massive torque to heavy driving wheels. The mismatch between turbine characteristics and railroad requirements demands a solution, and that solution determines the entire design philosophy. Reciprocating steam engines, the conventional approach, solve this through direct mechanical connection. Pistons drive connecting rods that turn driving wheels. The motion is violent, inefficient, limited by the physical constraints of metal moving back and forth hundreds of times per minute. Engineers had known for decades that turbines offered a theoretical path to higher efficiency. Continuous rotation instead of reciprocating motion, smoother power delivery, less wear on mechanical components. But the engineering challenges were immense. How do you condense the exhaust steam to recover water without adding crushing weight? How do you convert turbine rotation into the variable speed torque a locomotive demands? How do you make the machine reliable enough for daily service? The name that emerges from those 1924 Soviet journals is Anatoly Lomonosov, Russian professor of railway engineering exiled after the revolution, working in Germany through the early 1920s. His turbine locomotive, built by Maschinenfabrik Esslingen in collaboration with Krupp, represented the world's first serious attempt at a practical condensing steam turbine locomotive. The technical specifications were ambitious. A steam turbine rated at 2,400 horsepower at the turbine shaft. Turbine electric transmission to convert high-speed rotation into variable torque at the driving wheels. A complex condenser system to recover exhaust steam. The wheel arrangement, designated 2B plus B2, reflected the need to distribute immense weight across multiple axles while maintaining the flexibility to navigate curves. Lomonosov's machine ran on German railways between 1924 and 1926. Contemporary reports document the tests it moved. It pulled trains. It demonstrated that turbine locomotives were not merely theoretical exercises, but the official verdict was harsh. German railway officials deemed it too heavy for practical service. The condenser system, essential for efficiency, added so much weight that track and bridge limitations became severe constraints. British observers who inspected the machine noted its complexity. Maintenance requirements exceeded anything conventional steam engines demanded. Starting the locomotive required careful coordination between turbine operation and electric transmission. The machine worked, but it worked with difficulty, with compromises, with problems that conventional engines did not face. The pronouncement followed quickly. Interesting experiment. Admirable engineering effort, ultimately impractical. The Lomonosov turbine was labeled a failure, a cautionary example of theory outpacing practical reality. Within a few years, it was scrapped. The engineer's name faded from prominence. The history books, when they mentioned turbine locomotives at all, used Lomonosov's machine as evidence that the concept was fundamentally flawed. Yet, the technical journals remained in libraries, the patents were filed and recorded, the blueprints existed in German industrial archives. And 20 years later, when American railroads began building turbine locomotives, the designs looked remarkably familiar. Anatoly Lomonosov was not a dreamer chasing impossible machines. He was a professor of railway engineering who had spent years calculating the waste built into every conventional steam locomotive. Before the Russian Revolution forced him into exile, he had taught at the St. Petersburg Institute of Railway Engineers, training the next generation of designers. His lectures focused on a problem that frustrated him deeply. Reciprocating steam engines, the workhorses of every railroad in the world, threw away more energy than they used. For every shovel of coal burned, only 6 to 8% of the heat energy actually moved the train. The rest vanished into the air as waste heat, lost through the violent back-and-forth motion of pistons and connecting rods. Lomonosov's obsession centered on that inefficiency. In his published papers from the early 1920s, he argued that the fundamental design of reciprocating engines guaranteed waste. Metal pistons weighing hundreds of pounds had to stop, reverse direction, and accelerate hundreds of times per minute. That constant change of direction consumed energy. The impact of those reciprocating masses hammered the rails and the engine itself. Speed was limited by how fast the machinery could reverse its motion without tearing itself apart. Every element of the design fought against efficiency. Turbines offered a different path. Instead of forcing steam to push pistons back and forth, turbines let steam flow continuously through blades, spinning a shaft in one smooth direction. No violent reversals, no hammering impacts. Turbines in power plants already demonstrated efficiency levels above 20%, sometimes higher. If that same principle could work in a locomotive, the savings in coal and water would be enormous. But the engineering challenges were real and severe. A turbine needs to spin fast, thousands of revolutions per minute, to work efficiently. A locomotive needs to start from a dead stop and pull thousands of tons up mountain grades. The mismatch between what turbines do naturally and what railroads need was the problem Lomonosov set out to solve. Working in Germany after his exile, Lomonosov found partners willing to take the risk. Maschinenfabrik Esslingen, a respected locomotive builder, agreed to construct the frame and running gear. Krupp, the industrial giant, would supply the turbine and specialized components. The design that emerged in 1924 was unlike anything that had run on rails before. The turbine itself sat in the middle of the locomotive, spinning at speeds up to 12,000 revolutions per minute. Instead of connecting directly to the wheels, the turbine drove an electrical generator. That generator powered electric motors mounted on the driving axles. This turbine electric transmission solved the torque problem. The turbine could spin at its most efficient speed, while the electric motors provided the variable speed power the wheels needed. But efficiency demanded another innovation that added enormous complexity. Most steam locomotives exhausted their steam directly into the air after it passed through the cylinders. That meant constantly refilling the water tanks, limiting how far the locomotive could run between stops. Lomonosov's design included a massive condenser system that cooled the exhaust steam back into water, capturing it for reuse. This closed-loop system meant the locomotive could run much farther on the same water supply. It also meant carrying the weight of condensers, cooling equipment, and the pumps to circulate everything. That condenser system alone added more than 40 tons to the machine. The The completed locomotive stretched across multiple axles, its wheel arrangement designated as 2B plus B2 in European notation. Two small guiding wheels at the front, two sets of driving wheels powered by electric motors in the middle, and two trailing wheels at the rear to support the massive firebox and condenser equipment. The total weight exceeded 200 tons. The turbine was rated at 2,400 horsepower at the shaft, though transmission losses meant less power actually reached the rails. Testing began on German railways in 1924. The machine did what Lomonosov promised. It ran. It pulled trains. It demonstrated higher efficiency than reciprocating engines when operating at steady speeds. Crews reported smoother operation, less vibration, reduced wear on the track. At sustained speeds above 40 miles per hour, the turbine showed its advantages clearly, but the problems were equally clear. Starting required careful management of turbine speed and electrical load. The condenser system needed constant attention and absolutely pure water to avoid scale buildup that would destroy efficiency. Maintenance was complicated and time-consuming. Most critically, the weight created serious concerns. Many bridges and sections of track were not rated for a 200-ton locomotive concentrated on relatively few axles. German railway officials studied the test results and delivered their verdict. The technology was interesting but impractical for widespread use. The weight alone disqualified it from many routes. The complexity meant maintenance costs would far exceed conventional engines. The advantages in efficiency did not justify the compromises required. By 1926, testing had ended. The locomotive was set aside, then quietly scrapped. Lomonosov's turbine entered the engineering journals as a failed experiment, proof that some ideas work better on paper than on rails. The pattern appears first in Pennsylvania. 2 decades after Lomonosov's turbine was scrapped in Germany, Pennsylvania Railroad announced plans for an experimental locomotive that would eliminate the reciprocating engine entirely. The year was 1944, and the railroad committed substantial resources to what they called an independent development. Baldwin Locomotive Works received the contract to build a direct-drive steam turbine locomotive, a machine that would harness turbine efficiency for railroad service. When the locomotive emerged from Baldwin's Eddystone plant, designated Class S2 and numbered 6,200, the engineering choices were striking. A steam turbine mounted in the middle of the frame, a condensing system to recover exhaust steam. Turbine output rated at 6,900 horsepower. The wheel arrangement 686, distributed weight across driving wheels powered through reduction gearing from the turbine shaft. The approach to solving turbine-to-wheel power transmission differed in details from Lomonosov's electric drive, but the core philosophy remained identical. Use a turbine for efficiency, add condensing for water recovery, solve the torque mismatch through intermediate transmission. 3 years later, Chesapeake and Ohio Railway unveiled their own turbine experiment. 3 massive locomotives, designated Class M1, emerged from Baldwin Lima Hamilton's shops between 1947 and 1948. These machines returned to the turbine electric concept, nearly identical in principle to Lomonosov's 1924 design. The steam turbine drove an electrical generator. The generator powered traction motors on the driving axles. Each M1 was rated at 6,000 horsepower and weighed over 850,000 pounds with its tender. The condensing system once again added tons of equipment to recover exhaust steam. Chesapeake and Ohio engineers insisted the design was developed independently, yet the configuration matched the logic Lomonosov had published in German technical journals more than 20 years earlier. Norfolk and Western Railway completed the pattern in 1954 with their own turbine electric locomotive. Built by Baldwin, it followed the same philosophy. Turbine power converted to electricity, electric motors driving the wheels, condensing system for steam recovery. Each railroad claimed original engineering. Each development team presented their turbine locomotives as innovative solutions to railroad efficiency challenges. But the timeline reveals something the official stories do not. Baldwin engineers had documented access to German technical archives through industry connections established in the late 1930s. Pennsylvania Railroad's internal memos specifically requested European turbine literature before beginning their design work. Patent filings for these American turbine locomotives cited prior European art in carefully worded passages that acknowledged earlier experiments without naming Lomonosov directly. The designs did not appear from nowhere. They followed a path already mapped 2 decades earlier by an engineer whose name the new builders chose not to mention. The copying was quiet, careful, and remarkably complete. Pennsylvania Railroad's Class S2 entered service in 1944 with expectations shaped by years of development work and millions in investment. The locomotive proved what Lomonosov had demonstrated 2 decades earlier. At sustained high speeds, turbine efficiency exceeded anything reciprocating engines could deliver. Running at 100 miles per hour with 1,000-ton passenger trains trailing behind, the S2 demonstrated smooth, powerful operation. Track crews reported less rail wear compared to the hammering impacts of conventional locomotives. The turbine's continuous rotation eliminated the violent forces that reciprocating engines inflicted on rails and roadbed. Performance logs showed the machine could maintain speed and power for hours without the mechanical stress that limited conventional steam. But the same problems that plagued Lomonosov's design emerged immediately. At low speeds and during starting, the turbine consumed coal at alarming rates without delivering proportional power. The condenser system required constant maintenance and absolutely pure water. Any mineral buildup inside the condenser tubes destroyed efficiency and risked equipment damage. Maintenance crews discovered that turbine locomotives demanded specialized knowledge and tools that conventional steam engines did not require. The complexity translated directly into costs. After 5 years of testing and limited service, Pennsylvania Railroad retired the S2 in 1949. Only one had been built. The experiment was over. Chesapeake and Ohio's experience with their 3 M1 turbines followed a similar trajectory. In service between 1948 and 1950, the locomotives handled coal trains with impressive smoothness. The turbine-electric drive delivered power without the jerking starts and uneven force of reciprocating engines. At sustained speeds on level track or gentle grades, the M1s operated efficiently, pulling 4,000-ton trains without apparent strain. But operational reality proved harsher than test conditions. Variable speeds, the constant acceleration and deceleration of real railroad service, pushed the turbines out of their efficiency range. Coal consumption at anything other than optimum speed exceeded what conventional locomotives burned. The condensing systems required more maintenance than Chesapeake and Ohio had anticipated. By 1950, all 3 M1 turbines were withdrawn from service. Within 2 years, they were scrapped. The shared limitations across all turbine locomotives, from Lomonosov's 1924 original through the American experiments of the 1940s, pointed to fundamental engineering trade-offs. Turbines excelled at sustained high-speed operation where their efficiency advantages could overcome the weight and complexity penalties. But railroad service demanded versatility. Locomotives needed to start heavy trains, accelerate smoothly, maintain variable speeds, idle during switching operations, and handle these tasks reliably day after day. Turbine locomotives were optimized for conditions that represented only a fraction of actual railroad work. The final blow came not from technical failure, but from technological competition. Diesel-electric locomotives, rapidly improving through the late 1940s, solved the same problems turbines addressed without the complexity of steam systems. Diesel engines drove electrical generators that powered traction motors, delivering smooth variable speed operation. But diesels needed no boilers, no condensers, no water treatment systems. Maintenance was simpler. Fuel efficiency exceeded even the best steam turbines. Thermal efficiency reached 25 to 30%, nearly double what turbine locomotives achieved. By 1950, the future belonged to diesels. Steam turbine experiments ended not because the engineering was wrong, but because a better solution had arrived. The absence of credit in the American turbine locomotive projects was not accidental oversight. Multiple forces conspired to erase Lomonosov's pioneering work from the narrative. By the 1940s, Cold War tensions made citing Soviet-era engineers politically uncomfortable, even when those engineers had worked in Germany decades before the conflict. Lomonosov's status as a Russian émigré, his work published in Soviet technical journals despite his exile, created an association American railroads preferred to avoid. Beyond politics, there was engineering pride. Claiming independent development carried more prestige than admitting that a failed experiment from 20 years earlier had provided the blueprint. If the Lomonosov turbine was truly the impractical failure that contemporary reports claimed, citing it as inspiration would undermine the American projects before they even began. The silence served multiple purposes, all of them convenient for the railroads building new turbines in the 1940s. The physical evidence vanished as completely as the attribution. Lomonosov's original turbine locomotive was scrapped in Germany during the late 1920s. No components were preserved. No museum considered the machine worth saving since it had been officially declared a failure. Pennsylvania Railroad's S2 met the same fate in 1949, cut up for scrap metal less than 5 years after its construction. All three Chesapeake and Ohio M1 turbines were dismantled by 1952. Norfolk and Western's turbine followed the same path. Today, not a single steam turbine locomotive survives in any museum. Only photographs, technical drawings, and scattered performance reports prove these machines ever existed. The contrast with commercially successful locomotives is stark. Union Pacific preserved 8 big boys. Museums across the country protect conventional steam engines that represent successful railroad operations. But experimental machines, even those that influenced later designs, were erased when they failed to deliver commercial success. Patent documents tell the story the railroads would not speak aloud. United States Patent 2,458,461, filed by Pennsylvania Railroad engineers for their turbine locomotive design, includes careful language in its prior art citations. The patent references European turbine experiments and German condensing systems without naming Lomonosov or citing his specific publications. Baldwin Locomotive Works, engineers who traveled to Europe in 1937 and 1938, filed trip reports mentioning access to German industrial archives. Technical journal articles published by American railroad engineers between 1945 and 1948 discuss lessons learned from European turbine experiments, again without specific attribution. The coded acknowledgement runs through the documentation. The engineers knew. They studied the earlier work. They built on principles Lomonosov had established, but the official narrative insisted on independent innovation. The pattern extends far beyond railroad engineering. Innovation credit flows toward those who achieve commercial success, not those who establish principles. The experimental pioneer who proves a concept is possible but fails to make it profitable gets forgotten. The engineer who refines that concept 20 years later and brings it closer to viability receives the recognition. Lomonosov's turbine locomotives demonstrated that steam turbines could power trains, that condensing systems could work on moving locomotives, that turbine electric transmission could solve the torque mismatch. Those principles survived even as his name faded. Legacy is not written by who built it first, but by who built it successfully, and sometimes not even by them, but by those willing to claim the innovation as their own. The machinery we forget reveals as much about us as the legends we preserve. What other experimental failures are quietly shaping the designs we celebrate as original today? I'd love to hear your thoughts. Please leave a comment below and give this video a like if you enjoyed it. See you on the next one.